Okay, let's get started. So today we're going to be talking about transfer and reinforcement learning, and because this is a course on deep reinforcement learning, we're going to be focusing on topics that have been applied to large, scalable deep neural networks. Before we get started, a couple course reminders. So you should have already emailed us your project group and title by last week. On April 17th, we'll have a milestone report on your project and presentations on your milestone. We'll post more details on that on Piazza as it gets a little bit closer. And then on April 26th, shortly after, we'll begin project presentations. And then also starting on Wednesday this week, we're going to have guest lectures. So this is going to be the last lecture by one of the instructors in the course. And we have a great lineup of guest speakers, and it would be great for those of you that are not watching here for you to come and ask them questions because they're really leading researchers in the field. And for everyone here, you should also come. Okay, so before I talk about transfer learning, I'm going to talk a little bit about deep learning to motivate why we want transfer and why we want generalization in our agents. So there's been a number of success stories in deep learning for speech recognition, object detection, machine translation, just to name a few. And the reason why people are so excited about deep learning for these methods is that it works really well. And in particular, it can handle raw sensory observations, like the raw audio wave and the raw pixels, as the input, as well as the output, like raw letters for predicting what the speech actually was. And beyond raw sensory observations, it can also scale to the diversity of the real world. So there are real systems that are deployed using deep learning for doing these sorts of tasks, like speech recognition, object detection, and machine translation, where you can enter your own text or upload your own image, and it will perform the task for you. So it can really handle all the sorts of diversity that exists in real-world settings. And in this course, we've talked about how we can use deep learning for behavior, and in particular, using deep reinforcement learning for behavior. And one of the things that we've seen is that we can learn behavior, learn skills that map from raw sensory observations to the raw action space. And we can do this effectively. We can learn it from scratch, and it works well. But I don't think we've yet seen how we can learn behavior that scales to the diversity of the real world. And in particular, if you look at the deep reinforcement learning agents that we've been able to learn, they're all learned in very narrow simulated environments or learned for a single task in the real world. And in particular, there's this paradigm that in reinforcement learning that we're going to be training and testing on a single task in a single environment starting from scratch. And if we're only training on a single task and if we're always starting from scratch, we're not going to be able to scale to the vast diversity of tasks that we might encounter in the real world and the vast diversity of objects and environments that we might encounter. And so in this lecture, we're going to be talking about how we can transfer information from one task to another task. Why do we want to do that? Well, we don't want to start from scratch every time. If we want to be able to learn many, many different tasks, we don't want to have to learn all of them from scratch. We want to be able to use cheap experience in simulation in order to learn skills in the real world. So as we saw, sometimes reinforcement learning algorithms take many, many samples to learn. We can do this effectively in simulation, but if we want to actually apply this in the real world, it gets tricky. But if we can transfer experience in simulation for learning in the real world, then we can actually pretty easily use these algorithms to learn skills. And lastly, we want to be able to enable an agent to effectively act in an environment or in a scenario that it hasn't seen before. And if it can reuse its experience in some environments and with some different tasks, and then it sees an environment that it hasn't seen before or an object that it hasn't seen before, we want to be able to effectively adapt to that scenario and learn how to cope and learn how to act in that environment very quickly. Okay, so now that we've kind of set up the motivation, what is transfer? Transfer learning is something that's had many definitions in the literature. It's a very broad term. I was actually even hesitant to use it in this lecture, but I think that it's effective for getting across this type of learning and the types of things that we want to see. So for the sake of this lecture, the way that we're going to define transfer learning is as using experience from one set of tasks for faster learning or better performance in another task, in a new task that we haven't seen before. Okay, what is a task? We'll also have a broad notion of task. So task could be varying objectives, so the reward might change across MDPs. It might be varying robots, so we want to be able to learn on one set of robots, and then when we buy a new robot, we want to be able to transfer what we learned on those robots to the new robot. And in the MDP, this can affect the state, the action space, and the dynamics. And also, a task might refer to the environment. So we might want to be able to learn in some environments and then transfer what we learned in those environments to learning in a new environment. And of course, this can affect the observation space, the dynamics, and the reward. So effectively, we're trying to transfer knowledge learned in some set of MDPs to a new MDP that we haven't seen before. Does that make sense? Any questions? OK. And usually when you try to approach transfer learning, you make some assumptions about what will change across tasks to make the problem a little bit more constrained. We don't want to just say we're going to transfer from some arbitrary MDP to another arbitrary MDP, because that can be quite difficult, and maybe if it's completely unconstrained, then you can't really make any assumptions about the structure of those MDPs and kind of the structure that you can transfer from one task to another task. OK, and then another side note is that one thing you might ask is, well, why not just treat the whole world as an MDP and not worry about transfer? Then we can just have our agent go out in the world and learn in the world. This is a reasonable idea and generally could work, but usually it's more efficient to model what changes in the world. And generally, our reinforcement learning algorithms aren't powerful enough to just deploy them out in the real world and have them learn from very sparse reward functions and very diverse environments. And if we actually use the structure and model how the world changes in different scenarios, then we can get more effective and more efficient learning. OK. Now that we've defined transfer, let's go over a few different, some different terminology. So in transfer learning, we're normally considering the problem of transferring from one set of tasks to a new task. And so the initial set of tasks is called the source domain, and what we're trying to transfer to is called the target domain. That's the domain that we want to be able to effectively perform in after we've transferred. And then there's kind of three primary types of transfer learning, or types of generalization. The first is zero-shot generalization. And in this scenario, you don't use any data from the target domain. You just learn in the source domain, and then you want to be able to, like in 0 shots, without any information in the target domain, just be able to act in the target domain. This is very nice if you can just 0-shot generalize to new things that you haven't seen before. In many cases, it's somewhat limiting because you often can get some data in the target domain, and that can actually be useful to improve your policy. But it's still an important scenario. Second is few-shot generalization. So in this scenario, we get a small amount of data in our target domain. So like zero-shot generalization, we don't want to get too much data in our target domain, but we still want to be able to use a little bit so that we can effectively adapt to our new environment. And then lastly is just faster learning. So in this scenario, we just want to use less data in our target domain than training from scratch. OK. So now that we've defined transfer, how do we actually evaluate transfer learning? How should we evaluate how well learning transfers from one domain to another? The first thing to note here is if we want to do this on real robots, this is largely ad hoc up until this point. Usually, if you're dealing with real robots, you have the robot that you're dealing with is different from the robots that other people are working with. And so reproducibility is a big challenge. And so generally, you just consider a set of tasks that you want to start out with and a task that you want to be able to learn effectively and transfer to. And you define that on your own. And now if you look at some of the reinforcement learning benchmarks that we talked about in this class, the Atari Learning Environment and the OpenAI Gym, Both of these are very popular benchmarks and some of the most widely used benchmarks in reinforcement learning right now. But unfortunately, they don't evaluate for generalization. You're just given really a very narrow environment like Pong or Sequest in Atari, or for example, cheetah locomotion like you saw in your earlier homework. And you actually aren't evaluated on how well that agent can perform in an environment that's slightly different. It's evaluating for mastery instead of evaluating for generalization. And despite the fact that they don't evaluate for generalization, because they're so popular, a lot of people have tried to use these environments to evaluate methods for transfer, even though they may not be well suited for that. OK, so what about other benchmarks? So there's been a number of recently proposed benchmarks that have a lot of diversity and are proposing to evaluate for generalization and for transfer. Here are some of them. So the first one is Minecraft. This was introduced by Microsoft Research. It focuses on navigation and collaboration in the Minecraft simulated world. Second is DeepMind Lab, which was proposed last December for maze navigation tasks primarily. Also proposed last December by OpenAI was the universe. It's a wide range of video games, also the VizDoom competition, as well as ComAI, which was proposed by Facebook Research, which is communication-based tasks. And then also DeepMind said that they were going to release some StarCraft environment. And so a lot of these have a lot of promise for being able to evaluate reinforcement learning algorithms for transfer and for generalization. But generally, there's no consensus on actually, so I call these environments, not benchmarks, because really they provide a lot of environments for learning, but there is no consensus about actually how you evaluate how well an algorithm transfers or how well an algorithm generalizes across games. And so that's something that we still have to figure out. OK. So now that I've set that up, does anyone have any questions on transfer and these environments? Yes?
Is that open source?
So all of these are available for people to use. Not all of, so I think
the OpenAI released on GTA.
Yes, so I believe.
But it closed that.
Yeah, so some aspects of them are closed source where you can actually go in and edit the game. Some of them are, I think, very easy to edit it. So I know for ComAI, I think all the source code is available for that. I think you can also, for Doom, you could also edit the games. Some of them, I think, are more challenging to edit than others. And yeah, I'm not sure how many of them are open versus closed source. OK. OK, what's the kind of the first approach for generalization or for transfer? Well, what you can do is you can train your policy and then just try it on a new domain and hope for the best, hope that it works. And sometimes the policy will generalize and it will just work for those settings. For example, here's some videos of a policy that we learned on the PR2 robot here at Berkeley, and we trained it on the red coat hanger there, and we found that when we tried to transfer it to scenarios where there's distractors in the environment or different objects that we're trying to interact with, it was able to generalize. So here I'm holding the block, which is very different than the scenario that it saw at training time, but it was still able to handle these scenarios. Here Sergey is holding the bottle, and it's still able to, despite the fact that the scene looks very different, it's able to figure out how to do the task. But then sometimes it doesn't work. So for example, if you put a shirt on the coat hanger, it didn't work. If you put visual distractors near the object, it also didn't generalize. And so, yeah, sometimes things will work, sometimes things won't work. There's no reason to believe that it will succeed with enough variation. But it is, I mean, if you're running something, it is worth trying to see how far it will go. OK. So kind of the next approach, so the next approach here that I'm going to talk about is fine-tuning. So fine-tuning is something that's used a lot in the deep learning literature. And kind of the main idea is just to initialize with some network that's trained on some task, usually a task like ImageNet, and then fine-tune it on the target task. So train it, initialize the weights on a network trained on your source task, and then start training, usually with a lower learning rate, on your target task. And this works really, really well when you initialize with something like ImageNet and transfer it to other vision tasks. In practice for reinforcement learning, people have found that it doesn't work very well. And there's a number of reasons why, potential reasons why. I don't think that there's a clear answer, but the first thing is we don't have an ImageNet for behavior. So ImageNet is a very diverse data set. And in reinforcement learning, we don't have a very diverse environment that we can train on to get good generalization. And I think that if we had something that's more diverse, it might transfer well or better across tasks. Also, reinforcement learning, networks used in reinforcement learning tend to be much smaller than networks used in computer vision. And so there might be less representational power to transfer. And lastly, reinforcement learning algorithms are often very unstable at the beginning when they don't have any data to go off of. And so if your algorithm is very unstable at the beginning, then you might just have very large gradients that wipe out the initialization, and effectively you're starting from scratch. So we'll see, as I kind of go through different approaches for transfer today, fine-tuning will be a baseline for many of them, and we'll see that generally it doesn't perform well, and if we use more intelligent methods for transfer learning, we're able to outperform fine-tuning. And a couple of the approaches today actually will involve some amount of fine-tuning, but not kind of with the naive original approach of just training on a source domain and then fine-tuning from there. OK. So how do we achieve good transfer? I'll be talking about a number of different approaches under kind of 4 main themes in this lecture. So first, I'll be talking about how we can handle changes into the reward function by passing in a representation of the task. Second, I'll be talking about handling changes in the environment and the importance of diversity. Third, I'll be talking about using representations for effective transfer. And lastly, I'll cover some topics in meta-learning, which Sergey discussed a little bit in the previous lecture, but I'll go a bit more in depth. OK. So really the first approach, if you want to be able to generalize across tasks, the first approach that you can take is just pass in a representation of your task into your policy during learning, and then train across many different tasks. So the goal is going to be represented in the observation that's fed into your policy, and then you can train your policy across many different goals and hope that when it sees a new goal that it hasn't seen before, it can generalize. For example, in this figure, say you're trying to put the Lego block onto the other Lego blocks, or you're trying to put a ring onto a peg. In this diagram, what you might do is you might train on the red position. So you might train on kind of the corner positions of the Lego block, or kind of the corner positions of the peg, and then at test time evaluate on its ability on the green positions. So essentially interpolate between the positions that you trained on to evaluate generalization. And so generally this works. It's pretty simple, and you can get zero-shot generalization to new goals. But in practice, you need pretty densely sample different goals for good generalization. So as you might notice, the green positions are quite close to the red positions, and you have a number of red positions that you're sampling. And if you have many different axes of variation, and you're in like a higher dimensional space, then in practice it's going to be a lot more difficult to densely sample goals to get good generalization. Yes?
So you label these images with the green and red squares before you train?
No. So what's going on here is we first train a policy to put the Lego block here, and train a policy to put the Lego block here, 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 and here. And we feed in a vector representation of the goal. And then we feed in a vector representation of the center, and then run the policy. And it will then put it in the center position, or feed in a vector representation of here, basically the 2D position of the block. But good question. And likewise for here. So we'll train it on these 4 and tell it the pose of the peg, and then tell it to pose for this position, tell it to pose for this position. Likewise, you can also do this with vision. So you just you could place the peg at those 4 positions, and then if you place the peg at a new position within those 4 positions, it generally should be able to generalize to those positions. Yeah?
So in this example, like all those training goals and the transfer goals, they're kind of in the same domain. The only difference is they're at different squares.
Yeah, exactly. Yeah, so this is more a case, I guess, of generalization rather than transfer, perhaps, because there isn't any systematic difference between the domains. But in practice, when there is a large systematic difference between domains, it's pretty difficult to handle that case. OK. And the other kind of limitation of this approach is that often it can be hard to represent the task. So in this scenario, we can just represent the task by the 2D position of the peg or as an image. But in many scenarios, there might be multiple tasks that you want to do, like moving a chair, moving a laptop, and representing exactly how that task is supposed to be performed can be quite difficult. OK. And also, this approach is applicable to differing objects or differing dynamics. If you want a policy for screwing a cap onto a bottle, if you train on many, many different bottles, it should be able to kind of interpolate between bottles in order to generalize to new bottles. But in practice, training on many, many different bottles can be quite impractical. OK. So next, I'll talk about a case study, which is multitask learning on Atari. And so the motivation here is that, like this previous scenario where we're going to be passing in the task, we're going to try and train a single policy to work on all the Atari games. And because the Atari games are not densely sampled goals, because they are very far apart, it's going to be getting transfer and being able to benefit from training on all of them is going to be somewhat impractical. But what these approaches are doing is they're trying to say, OK, well, a human can play Atari with one single human, not just a different human for each game. And so can we train a single policy rather than an individual policy for each game that can play all the games? OK. And a note, in this scenario, you don't necessarily need to explicitly pass in the goal or a representation of the task, because the network can simply memorize what the game looks like and what it's supposed to do in those scenarios. And also, because it's memorizing that, in practice, it's actually going to be quite hard to transfer because it can simply classify the game and then kind of remember how to play that game. And if you're just memorizing which game that you're doing and kind of having a separate policy for each one, then you're really not going to have any hope for getting a benefit from training across all of the games. OK. So before I go about actually talking about how we will transfer across Atari games, I'm going to go over some background that these methods use, and particularly some background on machine learning model and ensembles and model distillation. And so what this is that when you're given a data set in machine learning, an easy way to extract knowledge from that training data is to train many different models on the same data set. And then once you train these many different models, then you can take the average prediction across those models. And so different models will have different biases and different tendencies. And if you start with, for example, different random initializations of the weights, different model architectures, potentially even different types of models, like neural networks versus random forests. And then if you take the average prediction, then this will kind of be able to allow the models to kind of take the benefit of each of the models and take the knowledge that each of the models have for the particular domain and the particular types of problems that they're good at solving, and kind of average those predictions into a single good prediction. And what this is called an ensemble over models. And ensembling is really how almost all machine learning competitions are won. because a single model might not be good at labeling all of the images in a data set or recognizing all of the speech in a data set, but across different models with different random initializations, different architectures, will be better at different types of tasks. The challenge with this is that at test time, because you have many different models and then are taking the average prediction, this is very expensive because you actually have to run your input through all of the models in parallel and then take the average prediction, which requires a lot of compute or a lot of time if you are more limited on compute. So the idea behind distillation is to take the knowledge from the ensemble and distill it into a single neural network, with the hope that we can actually do better than a single neural network trained on a single data set, trained on the data set. And the way that this works is that instead of training on actually what the network predicts, you're going to actually train on the soft targets. So if you're doing a multi-class classification problem and you have a softmax at the end, say ZIs are your average loadits over all of the models in your ensemble, you can actually get more knowledge from the network by actually using the kind of probabilities of each of the classes. If you only give, when you try and distill from an ensemble of networks just using their predictions and averaging over that, you're not really going to do better than just training on the data set. But what you can do instead is actually use the knowledge that's in each of those models, which is actually the class probabilities, which models actually the relationships between classes, and then train on the soft targets, train a single network on the average soft targets of the ensemble of networks to get better performance. And you can actually further soften by using a temperature, which will actually further show and further demonstrate the knowledge in the model. Yes?
So essentially what you're getting is you're getting these kind of average probabilities from an already trained ensemble model.
Yes.
And then you're training another smaller network.
Yep.
On these soft targets.
Yeah, so the question here was, just to clarify, we're training a network, training an ensemble of models, training many models on your training set. And then once you have that ensemble of models, you are training a single network, a smaller network, to essentially mimic those models and mimic the knowledge in those models.
Yeah, could you just explain that last equation again? So you have multiple models that each output class probabilities, and then you average the probabilities to get Z, then exponentiate it.
Yes.
And so then you have this new pseudo data set of P's and inputs.
Yep.
Okay, but then for that data set, it's not actual 0, 1 class, because you just have vectors of output.
You have probabilities.
Yeah, and then you
Then you take the softmax of that.
I see.
So the ZIs are the average probability over average logits over the ensemble of models, and then you take those averages and exponentiate and normalize to get a probability distribution over the class labels rather than the hard 0, 1 labels that the data set provides you, and then train a single model to output these probability values.
So the Y values are the PI that you train the signal.
Okay?
Yeah, so, and you were saying that the problem if you do a hard max and average over the hard maxes, then it's almost as if you were to train on the data set directly.
Yep. And so you can actually get more information and more knowledge by using the soft targets, because it's actually telling you kind of the relationship, what the ensemble learned about the relationship between class probabilities.
So then is this method only useful when you have this kind of notion of having a distribution over having class probabilities? Let's say if the network only output just let's a mean, let's say the distribution you care about is you're trying to estimate some Gaussian. In that case, can you benefit from this because it's you still working hard?
Yeah, to my knowledge, this hasn't been applied to continuous distributions. I don't know if Sergey, if you know of anything.
Not that I've seen.
Yeah, I've only seen this used on discrete output distributions. Yeah.
So you're averaging over the logits.
Yes.
What if they're different scales?
I think this.
The temperature is.
What?
I mean, that's what the temperature is throughout the scales.
So you average the logits to get the ZIs. I think I'm not 100% sure, but I think that when you average to get the ZIs, you average the post-softmax values. So after the softmax, they're all going to be sum to 1 for each of the individual models, and they'll all roughly be on the same scale. I'm not 100% sure, though, so you should double check that. OK, any other questions? OK, so this is how distillation works from an ensemble of networks. So how can we use this for multitask learning and for learning across different Atari games? And so what the two papers that I showed before, what they do is they train n DQN agents on n different Atari games simultaneously. And during training, they train a single student network to mimic the Boltzmann distribution of the DQN agent. So they essentially they train n agents on n tasks, and during training, at a single time point, they distill the knowledge of those n networks into a single student network that can hopefully be able to play all of the tasks. Yeah?
I guess, like, so for when you train, like, n agents on n tasks, like, you're getting some performance on those tasks.
Yep.
Like, just by averaging, like, the softmax over those tasks, like, actions, I guess, like, aren't you just, like, ruining performance on each and every task then? You're kind of, like, destroying performance.
Well, so the observations are going to be very different. And so it should be able to output different actions for different observations. So like the observation of a Pong image versus a Sequest image are going to look quite different. And you should be able to figure out the differences between those and then output the correct action.
Oh, so you're trying to, like, estimate the correct action given some observation.
Given the observation, yeah. And so how do you get the Boltzmann distribution? So instead of the ZIs with the logits, we're going to use the Q values to get this softmax distribution for our policy. And here pi e is denoting one of the DQN agents that's trained on a single task, so the E stands for expert. And then to distill it into a single policy, we're going to use the KL divergence across all of the tasks, and essentially use the same distillation objective to train across actions for discrete action spaces to mimic the distribution of the expert network. And so kind of what this looks like as a diagram is you use DQN to train the teacher networks across each of the individual tasks, load up the experience into your replay memory. So this is done for all of the n tasks. And then use a distillation loss as supervision to train your student network to play across all of the tasks. Yeah?
But the tasks have different action spaces. How does that work?
I think that they just put it into some vector representation that
There's a finite number of buttons.
yeah, I mean, so your action space is finite length, and you can just kind of put it within that. There may be parts of the action space that aren't used for some tasks if it has a smaller action space.
It kind of works as well or as poorly as it's exactly what you think it is.
Yeah.
So just like a higher level question. I guess the reason why you're doing this is because you actually believe there's some information that can be shared across tasks. So like, would it be reasonable to just try to build like a hierarchical Bayesian model for that? Because that'd be also like a very natural way to like sort of share like statistical strength between different tasks. I mean, I don't know, maybe it just wouldn't work very well because like it might be hard to put deep nets and all those things. But that
Yeah.
also seems like a very natural way to do it. This is like a little bit, you know,
Yeah.
messy.
Yeah. Yeah, it's a bit messy. And I'll talk a bit about the limitations in a couple slides. I'll talk a little bit more about, well, I'll talk more about how we can do better ways for transfer. In practice, I think that they use supervised learning because it's very stable. And that's one way that you can get transfer across tasks. I'll talk more about the limitations in a minute. Okay, so how well does this do? So in the Toronto paper, they trained this across 8 different tasks that are shown here. the blue network shows the single policy, the single actor mimic policy that was learned across all tasks. And the red curve shows the separate expert DQN policies. And what you can actually see is that actually on some tasks it is able to outperform the expert DQN policy. So on Breakout and on Atlantis, for example, the blue curve is able to exceed the return of the red curve. Whereas in some scenarios it actually does worse, which isn't too surprising, so on Sequest and on Crazy Climber. But it is able to generally learn how to do these sorts of tasks. Yeah.
What's on the x-axis?
The x-axis is training iterations times 10 to the 6th or something. I don't know the exact scale, but it's, yeah, training iterations versus average return.
So after the student policy is already trained, then it gets trained again?
So the student policy is being trained while the expert policies are being trained. And so this is, the x-axis is just showing like the raw amount of experience, like the number of frames that both agents have seen.
On that one game, but the student has
Yes.
more frames overall?
Yes, so the student has seen actually, yeah, 8 times the number of frames. Yeah.
I'm not sure about the setup. So how is it starting at near the top for like boxing and almost for breakout? How's the actor mimic policy like? Almost perfect from 0.
Well, is this the ones on which it's trained, or are these generalization?
This is just what it's trained on. There isn't any
Well,
generalization.
That's probably why it's starting at the top, because it's already been trained on that.
So it's like,
Well, but they're both starting from scratch. They're being trained simultaneously.
Oh.
I'm not sure.
okay. I mean, are these learning curves like, are they like already pre-trained on the expert policies and then sort of like?
No,
Um,
they're trained simultaneously.
okay.
But yeah, I'm not sure.
So you do like just like 10 DQN updates on each of the expert network, and then you do like one sub-supervised learning on the student network.
Yep.
Okay.
Okay. So now the pros and cons. So the pros is that we can learn a single policy for multiple tasks. The limitations is that we still need to train on each game generally for the same amount of time. We don't get any benefit. And the performance generally drops slightly from multitask training. And there isn't a lot of transfer that you get a lot of benefit by training across tasks. But kind of the caveat here is that I don't think Atari games are good for transfer. They're very different, and the observation space looks very different. The action space is very different across tasks, and I think that with more similar tasks and more similar environments, we can hope for better transfer. And so I don't necessarily think that's the approach that's preventing transfer. I think it might be actually more the environment. Okay, so how can we do better than this? I'm going to touch on one last point on kind of this topic, which is memory. So this is a paper that was from ICML last year, and what they found is that if you're using a feed-forward network to train across many different tasks, it might be forced to memorize different training environments. And also, like the wrong memory, if you do introduce memory into the network, the wrong memory mechanism might also lead to memorization and lead to worse generalization performance. So they were focusing on the Minecraft domain, which is, I think, more applicable to transfer and generalization than the Atari games. And they showed that you can improve generalization with the appropriate memory mechanism. So they compared several different DQN architectures. The first was just a feed-forward network that takes in a sequence of a past history of frames. The second one was just an RNN combined with DQN, so it's a recurrent network, I think, that used an LSTM to represent the Q network. And then they also tried out 3 different architectures for networks with an explicit memory module. And then in kind of the latter 2, they experimented with adding recurrence to the context that's being fed into the memory, and also adding in a connection between the memory back to the context. And they trained these networks on several different tasks in the Minecraft domain. So I'm going to show one of them here. So in this task, the goal was to look at, it was a first-person view of the environment. This is a top-down view of the environment. And the goal was to look at these two patterns. And if the patterns were the same, it was supposed to go to the red square. And if the patterns were different, it was supposed to go to the blue square. So it was, and then what they did to evaluate generalization is they had different patterns here that were not seen during training, and they randomized across many different patterns to evaluate transfer and generalization. And so they trained each of these 5 networks on evaluating both for the training scenarios as well as unseen scenarios. And they found that, well, first, DQN wasn't able to even do well on the training set. It wasn't able to, because it requires a bit more memory than, actually in this scenario, well, because it was simply just trying to memorize the environments, it wasn't able to perform well. And likewise, actually, the recurrent network also wasn't able to figure out how to do this task. Then the second 2 memory mechanisms were able to do pretty well on the training scenario, but generally were overfitting and not being able to perform well on the unseen scenarios. Whereas using the last memory architecture, they found that it was able to very well perform the training examples and also generalize fairly well to unseen scenarios. And so I think the takeaway here is that with the appropriate memory mechanism for your task, if you give the model the type of mechanism that makes it easy to learn how to remember things and how to retrieve things from memory, then you can see good performance and good generalization across a number of environments. Yes?
So how is this memory usually implemented, say, in neural net?
There's a number of ways that you can put memory into a neural network. Some of them so there's a couple popular things that have been used, like the neural Turing machine and memory networks, which is proposed by FAIR. I don't want to go into the details of how the memory is used today for the sake of time, but I encourage you to look at the paper. Yeah?
What's context?
Context is just an encoding of the observation. OK, so kind of the takeaways, this is using memory is something that's easy to combine with other approaches that you want to use for transfer. Some of the limitations, well, one limitation is generally it doesn't completely solve the problem, and next we'll talk about ways that we can get even better generalization. OK, so we just talked about how we can handle changes in the task and handle changes in the reward function. What about changes in the environment, in particular changes in the observation space? So one of the big interesting problems in transfer learning is being able to transfer from simulated environments, from experience in simulation, to experience in the real world. And I'm going to talk about, well, I'll talk about 2 main approaches for this, two approaches using diversity. So the first is a recent paper from Berkeley, and what they were trying to do is they were trying to have a quadrotor be able to fly through an environment and avoid obstacles. So what they did is they trained the quadrotor in simulation across many different environments with varying hallway geometries and varying textures. And they trained it to predict whether or not, if you took a sequence of actions, whether or not you would collide in the future. And then when they wanted to take actions, they then took actions that would prevent collision in the future. So a pretty simple RL setup. The interesting thing here is that even though the simulations on the left aren't particularly high fidelity, because there was a lot of variation across textures and across hallway geometries, they were able to show without any experience in the real world, they could use this architecture and apply it in a real world setting on real images to be able to avoid obstacles in the real world using a real quadrotor. So here's some example of flying through a small maze. There's also examples of going through sharp turns. And so the top is the view that the quadrotor is seeing, and the red is the steering command. And the bottom is the third-person view of the quadrotor. And here you can actually see that it's going to choose to fly through the window, I believe, and then fly up the stairs. And so the really impressive thing is that without even seeing a single image in the real world, it's able to just take experience in simulation and transfer directly. Okay, and so there was actually another paper that, inspired by this approach, actually applied this for object localization, particularly for the use of robotic manipulation. So what they did is the goal was to be able to localize different shapes of objects seen here in the real world. And what they did is they trained in simulation across many different object colors, many different lighting setups, and many different camera angles, how to localize objects in simulation. And then, like the other paper, just be able to apply it directly in the real world without any real world images. And they also found that it was able to work quite well. So here, the goal is to reach a certain object shape. In this case, it's the hexagon. And then in a moment, it's now the cube that it's trying to reach. And it's able to accurately localize objects and use a hard-coded controller to pick them up. And OK, well, you might look at this and say, OK, how much diversity is needed? And so they trained on many, many different unique textures and showed that actually the more unique textures that you use, the lower the error was for localizing the object. OK, so the benefits of just training and simulation with a lot of diversity is that it works surprisingly well. You can get zero-shot generalization to the real world without actually seeing any images in the real world. The limitations is that first, content creation in simulation requires a large engineering effort. So actually creating a lot of, you can do this with textures and with geometries fairly easily, but if you want to do this with many different tasks or many different environments, it can become a larger and larger engineering effort the more kind of diversity that you want. And second, they were able to get zero-shot generalization, but they actually don't use any target domain data. And actually, there's probably, if you were able to get a few real-world images, there's actually probably a lot that you can do to try and make the domains align to each other using techniques from, for example, domain adaptation. And then lastly, thus far, this has only been demonstrated for shift in the visual observation space, not yet for differing dynamics or differing reward functions. I think that we'll have to see if this works for differing dynamics. I think that dynamics might be a bit more tricky because you actually accumulate differences across domains if your dynamics are systematically different. OK, yes?
How do they pre-train an environment that say it will collide or it will not collide?
How do they pre-train what?
So how would they know that you're going to collide on something, given there's only a picture?
So in simulation, what you can do is you can actually just run those actions forward. So if you're in simulation and you have just some scene, you can just run actions forward and see if you collided. Because in simulation, you know kind of the ground truth state of the world. You can't do this in the real world, of course, which is why it's very, well, you can, but you might end up crashing your quadrotor a lot. And that's actually one of the big benefits of simulation is you don't have to worry too much about safety when you're learning.
Oh, but there's also an action that's input, that like the collision is for an image
Yes.
and an action.
Yeah, so this collision model is predicting, given the initial image and the sequence of actions, after those n actions, will you collide or not?
So they actually got a simulation software instead of just raw images.
So they used a simulation software that was able to render out the scene. And so it's using both the rendering from that simulation as well as the actual physics simulation. Yeah?
But then you effectively also have transfer and dynamics, right? Because the dynamics are different from the simulated environment. I mean, the quadrotor behaves differently.
Yeah, so the quadrotor, generally will behave differently in simulation in the real world. I think that the way that they represented the action space, they were able to align it fairly easily and fairly well. Because if you're, I think that they use something like velocity control, where you're just measuring, you're just outputting kind of what velocity you want to move at. And then kind of velocity is something that behaves actually similarly in simulation as well as the real world, if you actually can achieve that velocity. Yeah.
Yeah, so, yeah, kind of like to his point where he said, like, there's no, like, alignment of, or there's no, like, trained alignment between action spaces in these two domains. Like, do you know of any work that's, like, concurrently doing, like, alignment in state space and action space?
So are you meaning, is there any work that's trying to transfer the dynamics as well?
Yeah, dynamics as well.
Okay. So I do know that there was some work by Igor Mordach at about a year ago on transferring for a Darwin robot, and then there was also some work, some recent work at OpenAI on learning an inverse dynamics model to be able to transfer from dynamics in simulation to the real world. And those are the two that I'm aware of. I don't know if Sergey, are you aware of more?
There's also work on non-deep
yes.
that looks at things like manifold alignment for trying to put systems actually with different action spaces into correspondence.
Yeah, and a big keyword there is system identification, to identify the system that kind of the dynamic system that you're operating under. Okay, with that, we'll take a short 2-minute break before moving on to ways to reuse representations. Yeah.
In your experience, for like DQ, it's completely independent from this, but from training like deep policies, for example, for the homework, when you have to implement a neural net to
Yeah.
feed forward, right? You start off with something like 3 layers. You decrease the number of hidden units. You use Atom or something, right? Are you aware of any like good structures to start with in current networks, like LSTM? What would you use as like a first try to then fine tune?
Yeah. So there's been some recent work on studying what memory architectures are good for reinforcement learning. I think that the Michigan paper that I went over could be a good place to start. So I think that the memory mechanisms that they used were, so they found that the recurrent network just in LSTM really didn't work very well. But I think that the memory mechanisms that they used with DQN were working well for them. So I would look at it's a Michigan paper. Hung Luk Lee is the last author. I think it's O et al.
So they use feed-forward networks with some special memory mechanism.
They have a memory mechanism that looks, I think it looks somewhat like a neural Turing machines, where you have like this external memory that you're reading and writing to. Yeah, and I think that those work well. I think that there was also a recent paper that was like actually like studying different memory architectures for reinforcement learning.
You'd say it's better to look at these memory architectures than typical recurrent networks like LSTM.
Yeah, I mean you can start with an LSTM. It might work well.
Kind of doesn't.
Yeah. So I would look at the Michigan paper because they found that the LSTM didn't work well, and they found things that did work well.
Okay, cool. Thanks.
Yep.
What's the title of the multitask deep reinforcement learning paper?
So it's actor mimic and policy distillation.
Oh, actor mimic and policy.
There's two papers. Policy distillation is the DeepMind paper, and actor mimic is a paper from Toronto by Emilio Perry Soto. Yeah, Russ Selikoudinov is on that paper.
Okay, great. So what do you think about the largest? Is that a good way to regularization, or it contains a dark knowledge?
Yeah, so using soft targets is a good method for regularization. And actually, in the dark knowledge paper, they showed that if you actually just train on soft targets, if you actually soften the targets in a data set, you can actually get a regularizing effect.
So did they try, like for example, in this paper, they kind of use the ensemble model, and after training all these models, and then they do positive distillation over the ensemble model. But why do we just train the model alongside? Like, I mean, use the soft target, soft targets. I mean, that one is a regularization term while training this individual model.
They do train it while training the individual models. They do it like they train them simultaneously.
Oh yeah, I mean, but in that case, the different models do not communicate with each other, right?
Yes.
So, but what I was proposing is like, can we use the regularization term of the soft logics, the soft targets as the regularization term while you train the individual models? Is that a good way to try?
Yeah, I think that if you tried to,
That could make sense. So
you
there's been a tiny bit of
you could. I'm not sure.
work on
I haven't seen soft targets used with reinforcement learning algorithms before.
Oh,
So I don't
mean,
know.
like during training and
Yeah.
using that one. Okay.
But it could be interesting to try.
Okay, sure. Okay, thank you.
We'll just finish something else.
Okay, let's get started again. So now we're going to talk about ways that we can try and reuse representations for transfer across different tasks. And in particular, I'll talk about 3 different approaches for doing so. Starting with progressive networks. So the way that progressive networks works is that, say we want to transfer from one task to another task. So we start by training on a single task or a single domain that we're going to start with learning. Then we freeze the weights of the neural network that we're learning for that domain. And then reuse the frozen representation on that domain while also training a new network on a new domain. So you reuse the representations, the frozen representation of the source domain, and while also training a network with some new representations in the target domain. And then you can repeat this for new domains. So visually, the way that this works is, say red is your source task and blue is your target task. You first train a task on your source task. This is shown as the red neural network. Then you freeze the weights of the intermediate representations of that network. And then when you're training on your target task, you both run that observation through your original network as well as through your new network, and then concatenate the representation from the source domain to your representation at the next layer, and then likewise at higher levels as well. And in particular, you don't continue to train the network on the source domain. You keep that fixed. And the blue boxes are free weights. So those are also, the parameters of those networks are optimized. And then once you have 2 tasks trained, you can further train a third task by freezing the weights of the second network that you trained, and then concatenating the representation from both of those to the representation that you're learning on your third task that you're trying to learn. Does this make sense? Any questions? So it's quite a simple approach. They tried this on a couple different things. So the first thing they did is they tried this on variations of Pong. So the kind of the normal Pong is shown on the top left. The bottom left is a version of Pong where the colors are inverted. The bottom right shows the score is moved to the bottom. I think they just like flipped took the mirror image across the horizontal axis. And then they also tried a Pong where the image was moved slightly. So what they did here is they're showing the learning curves where the x-axis is the number of steps and the y-axis is the score. And when they train on the white game, if they train from scratch, that's the lower learning curve. If they just try and fine-tune from the normal Pong, it does slightly better, but it's still fairly slow to learn. And then if they use progressive networks, that's shown as the red curve. And they show that they're able to effectively transfer from normal Pong to the white version of Pong. And then likewise with the horizontal flip, actually fine-tuning and just training from scratch work fairly well. Actually, so I think the black curve is not training from scratch. It's a different baseline because it would be a lot slower. But the with progressive networks is able to outperform baseline models on these tasks. I think the baseline model is the baseline here is a different version where you essentially take progressive networks, and instead of starting from a trained network on the previous one, you start with random weights on the left side, on the first column. Okay, so they also tried this with transferring from Pong, River Raid, and Sequest to boxing. So here are the two baselines. The yellow curve is showing just transferring from Pong to boxing. So it actually doesn't really get much benefit from training on Pong and then trying boxing. The orange curve shows transfer from Pong and River Raid. And the red curve shows transferring from Pong, River Raid, and Sequest, which actually does slightly worse than training from Pong and River Raid. So it seems like River Raid is very effective for transfer. Okay. They also train this on a simulation to real world scenario where they're trying to have this Jaco arm, which is shown on the bottom, be able to reach a red target position. And they first trained it in simulation, used that for the first column, and then reused the representations learned in simulation for learning in the real world. Here, because they use a very sparse reward in the real world, it wasn't able to learn at all when you train from scratch. If you fine-tune, that's shown in yellow. And so it is able to learn more quickly, but it isn't able to kind of hold its performance. And using progressive networks, it's able to effectively learn the task more quickly. Okay. So kind of the pros, it's very effective and simple approach. The limitations is that it's somewhat dissatisfying in that the network isn't going to grow larger and larger as you get more and more tasks. And also experience in the new domain isn't going to help the old domain. So it's somewhat asymmetric in that manner. And lastly, learning, especially on the Atari games, is still fairly slow, although that might be mostly an attribution of an effect of the algorithm being slow rather than the actual method for transferring. Okay. Any questions on progressive networks before we move on? Yeah.
If you return to the old domain, though, you would improve it. The old domain on that.
Actually, yeah. So one thing you could do is so this is your like original domain. I guess you could then freeze the weights of this and fine-tune this, although you would have to then kind of concatenate these representations to, I guess, well, you could just like now train a fourth column on your new domain, for example, and potentially improve. Okay. So next is PathNet. So PathNet is actually kind of something it's very similar to progressive networks, and it mostly is focusing on how we can remove the need for the network to grow larger and larger and larger as we add on tasks. And the main idea is that instead of kind of having this fixed relationship between columns where you just concatenate it and retrain new weights, instead we're going to evolve relationships between columns. And so the way it works is you pick a new task, evolve a path through the network for that task, and learn weights along that path. And then freeze the weights only along the evolved path for that task. And then repeat, only changing the unfrozen weights, not the weights that are along the path that was evolved for that task. So effectively, they're using a genetic algorithm to select paths, so which parameters to train for that task, rather than having a fixed column like in progressive networks. And they use a gradient-based reinforcement learning algorithm like you've learned about in this class, to actually learn the weights along that path. So what this looks like visually is starting at the top left. So they randomly initialize a population of paths. And then from kind of going downward, they start on learning Pong. And it learns a path for Pong, which is shown in light blue at number 4. And then they freeze the path and the weights for Pong. So that's shown in red at step 5. And then once they freeze the weights for Pong, they reinitialize a population of paths for learning Alien, and then evolve the path and learn the weights simultaneously for the new game Alien. And those are shown in blue in the final image. They showed that this is able to work well for transfer from River Raid to other games. So it seems like River Raid is a game that's useful for transfer in general. So here, red is training from scratch, green is fine-tuning, and blue is using PathNet. And in many scenarios, it is able to get some benefit from transferring. Okay, so the pros over progressive networks is the network size is fixed, so we don't need to have, and it's straightforward to grow it if needed. You can just add some more weights. It's an effective combination of evolutionary and gradient-based learning. And then kind of the limitations, learning is still slow, as in progressive networks, and again, experience in a new domain doesn't help old domains, although you could go back and train on your old domain if you want. Okay, and then the last piece of work on reusing representations that I'm going to talk about is modular networks. And this is somewhat separate from progressive networks, somewhat different. And the main idea here is that we're going to try and transfer across different robots and different tasks by training a module for each robot and for each task. So kind of generally in reinforcement learning, you have one policy for learning one robot and one task. But if you want to learn across many different types of robots and many different types of tasks, you want to be able to kind of get away from just training a single policy for each combination. So what they do in this work is they train a module to be task-specific and a module to be robot-specific, such that you can reuse the robot-specific module for different tasks on that robot, and reuse the task-specific module for that task on different robots. And so kind of the way this works is you train the task module and the robot module for different tasks and different robots. For example, you might have a 3-link robot versus a 4-link robot, or a task where you want to push an object versus opening a drawer. And the key to getting this to work, so if you just kind of train this naively and train them in a way that you would normally train neural networks, then these modules will tend to overfit to each other and kind of just pass in information across information about the robot included in the task module, and it'll include information about the task in the robot module. But you want them to be more separate. And so that to get this to work, they use dropout and a bottleneck at the connection between these modules. So they limit the amount of information that can pass through here so that it is forced to only represent information about the task and information about the robot. Yeah?
So I can see how you can, I guess, cause an information transfer, like you can minimize the information transfer.
Yeah.
But how can you guarantee that like the first module is necessarily specific to the robot and the second one is specific to the task? How do they enforce?
In practice, I think it's hard to guarantee it. You can just do as much as you can to try and encourage that to be the case.
So like would they like, for example, like maybe like try different combinations of robot and task? So like
Yeah.
hold the task fixed and then change.
Yeah, so generally you will train across robots and across tasks, such that you do have to, I mean, if you just train this on a single task, it won't know that, or if you just train, the robot module on a single task, it won't know that it's supposed to be general across different tasks. So kind of in practice, what they do is they This is reach, push, and peg insert are showing different tasks, and each of the columns are showing different types of robots. And you train on different combinations of these, and then hold out one of the combinations, and try and see if you can kind of just generalize to this scenario by like selecting the right task module and selecting the right robot module. Did you have a question?
I mean, what I wanted to say was that if you're sharing the networks and you train on a number of combinations, then
Yes.
you can kind of
Yeah.
guarantee the decoupling.
Yeah, so that's what they do.
So just one more question. How
Yeah.
would that help you if, I guess would it be impossible to just have like this one network again and just train it on, I guess because the robots have different action spaces. So
Yeah, the robots have different action spaces in this case. Yeah, and also the tasks are different. Okay, so this is one of their experiments. So they had reaching, pushing, and inserting a peg, and a 3-link robot, a 3-link robot with different lengths of links, and a 4-link robot. And they showed that if they trained on these 8 different combinations, they were able to generalize to a new combination, namely this combination, in 0 shots. So they just took the task module for pushing and the robot module for the 4-link robot, put them together, and they were able to get 0-shot generalization. It was able to work for that task in that robot, which is quite nice. They also trained this on a set of harder tasks. So in this case, the tasks were pulling a drawer to a target location and pushing a block to a target location, and then they used a 3-link, 4-link, and 5-link robots. In this scenario, they trained on 8 combinations and tested on the held out combination. And in 0-shot, it wasn't able to perform exactly well, but the initialization was a good initialization for the task. It was generally kind of close to performing the task, but wasn't able to do it in 0 shots. But with some training on that target task, they were able to effectively perform the task with a little bit of training. In this case, with 10 iterations of training. They use guided policy search here for the policy optimization algorithm. Okay. So kind of the benefits here is that you can get this interpretable representation of kind of robots and tasks. And you can achieve 0-shot generalization in some cases. If not, you can just fine-tune on your target task to get good performance on the target task. The limitations is that you need to limit the information passing and regularize the network in order to get this modular effect. And in practice, it's hard to guarantee that this will actually happen. Yeah. Any questions on modular networks before we move forward? Okay. So next we'll be talking about, can we learn to adapt quickly? And in particular, we're going to see if we can use meta-learning to learn how to adapt to new environments by using the structure across tasks. So generally, the idea of meta-learning is that we're going to try and learn across tasks and identify the structure across tasks such that when we see a new task from that distribution, we can learn very quickly. So this is somewhat similar to reasoning or representation, except we're actually going to explicitly train for the ability to adapt to a new task or to learn to a new task from our distribution. There's been a large body of work on meta-learning. Kind of the main approaches that have been used for this are learning and update rule for our learner network, Bayesian modeling of each of the tasks, as well as memory augmentation, just throwing a network with a lot of memory and trying to have it kind of figure out the structure across tasks. Pretty much all of this literature is in supervised learning settings, like few-shot image classification or trying to learn how to optimize a neural network more quickly than we might before. But we can also do this for reinforcement learning and try to use meta-learning to learn faster reinforcement learning algorithms. So this is exactly what a couple papers did that very recent papers did, and kind of the key idea here is they're going to try and train a recurrent neural network to learn how to solve new MDPs. So what this looks like is the reinforcement learning algorithm is going to be a recurrent neural network and some generic computation architecture. And the different weights, the different activations in the recurrent neural network will represent different reinforcement learning algorithms. Oh, sorry, different weights in the recurrent neural network means a different reinforcement learning policy, and different activations mean the current policy is going to be different. So the way this works is that you train your recurrent network on a sequence of episodes in an MDP and train it on a sequence of MDPs. And crucially, you don't reset the hidden state across episodes in a single MDP. So the recurrent neural network is learning how, given a single episode, how to improve from that episode to the next episode, and so on. And then you're training it across several different MDPs such that when it sees a new MDP that it hasn't seen before, it can learn quickly, given fewer episodes than you would need to learn from scratch. And this actually, one thing to note here is this is actually quite similar to the memory approach that I talked about with Minecraft with maze following. So if you're trying to solve a maze, what you might do is just kind of give it a recurrent neural network that's trained to kind of look at the maze and explore the maze and figure out where the goal is, such that in the future, it can actually reach the goal much more quickly if it's starting from the same place and the goal is in the same place. And so these papers, first they compared to asymptotically optimal algorithms on bandit problems. There's been, I don't know if we covered this in this course, but there's been a lot of there's a lot of literature on solving bandit problems, which are essentially reinforcement learning problems where there's only a single time step. And there's a number of algorithms for solving bandit problems using Gittins indice, Thompson sampling, and upper confidence bound. And they compared a reinforcement learning algorithm learned using meta-learning to these asymptotically optimal algorithms, and we're able to find that on these correlated arm bandit problems, it was able to perform as well as these algorithms. Here on this graph, they trained on a medium difficulty bandit problem and tested on a harder set of bandit problems. Essentially, bandit problems where the arms are less correlated with each other. Okay. I'm running a little bit low on time, so I'll move through this fairly quickly. They also trained this on maze navigation in Doom. So before meta-learning, it isn't able to learn very effectively. So the left is showing the first-person view, and the right is showing the third-person view of the agent moving through the maze. And it is able to make some amount of progress towards the goal, but generally learning is very slow because, as we know, reinforcement learning algorithms aren't that fast yet. But after meta-learning, it's able to effectively learn on new mazes. So here you show the path, and so first it kind of looks over here, doesn't see the goal, looks at the top, doesn't see the goal, and then goes to the goal. And then after it's seen that first episode, it knows exactly how to go straight to the goal. So it's a very, very fast reinforcement learning algorithm for maze navigation in particular. Okay, so kind of some of the benefits of this is a very simple approach. You can just apply a recurrent neural network across many different problems and learn new tasks from the distribution of tasks seen during training. Some of the limitations is asking a lot of the LSTM, so trying to actually put a reinforcement learning algorithm into a recurrent neural network is asking a lot from these sorts of memory architectures and can be quite challenging to learn in practice. And also, it might not be able to handle tasks from outside of the distribution very well because at test time, you're actually just running this LSTM forward, and it might kind of overfit to the sorts of tasks that it saw at training time. You're not just running a reinforcement learning algorithm at test time. Okay, and so the last thing that I'm going to cover pretty quickly is how we can try to learn few-shot adaptation and reinforcement learning. And this approach is largely building on top of fine-tuning. So in fine-tuning, say you have some pre-trained parameters theta. What you do is if you have your new task t, then you're just going to run gradient descent from your pre-trained parameters on your new task. Well, how do we do this for behavior? In vision, theta would be parameters that are pre-trained on ImageNet, but in reinforcement learning, we don't have an ImageNet for behavior. So what we want to do is we want to actually learn some features, learn this representation that's effective for transfer across many different tasks. So what we want to do is we want to be able to do fine-tuning at test time for a new task, a new reinforcement learning task that we have. And so what we're going to do is we're actually just going to backpropagate through this fine-tuning procedure to find a representation theta such that it transfers well across many different tasks. So what this optimization method looks like is we're going to optimize for this theta such that when we take one or a few gradient steps with respect to our task, we get good generalization performance on that task. And so kind of the key idea is to train over many tasks to learn a parameter vector theta that transfers well. So here's our equation. Kind of pictorially, what this looks like is theta is the parameter vector that's being meta-learned. Theta star is the optimal parameter vector for task I. And during meta-learning, we're learning this representation theta. And when we're at here during meta-learning, if we take a gradient step with respect to task 3, we're quite far from the optimum. But at the end of meta-learning, when we take a gradient step with respect to each task, we're quite close to where we want to be. And this is called model-agnostic meta-learning. And so this is tried out on a number of locomotion problems. First was running at a goal velocity. And second was either running forward or backwards. So in this case, there's only 2 tasks. The meta-learning was done with TRPO. That was solving that minimization problem we saw on the previous slide. And the learner was using vanilla policy gradient or reinforce. Compared to 3 baselines, the first is an oracle, which provides an upper bound. Second was pre-training on all the tasks and fine-tuning from there. And the last is just random initialization. And each of them get 20 rollouts for the learner update. And what the results look like is after 0 gradient steps, here's the policy that's learned. And then after 1 gradient step, it's able to very quickly learn how to adapt its behavior to run at a goal velocity of 0 or a goal velocity of 3 in this case. Whereas if you start with just a pre-trained policy, it isn't able to quickly adapt to different goal velocities because it wasn't trained to do so. And then likewise, we can do the same thing for running forward and backward. So this is the task, the policy before any gradient updates. And then just after a single gradient update, model-agnostic meta-learning is able to learn a policy that quickly is able to adapt its behavior to go forward or to go backward. Whereas random initialization isn't able to effectively achieve these sorts of gates. I'll skip over this. And then you can also actually apply this method to supervised learning problems and compare it to a lot of the literature that I mentioned before. And it turns out actually that this method is able to outperform those methods on the few-shot image classification problems. OK, so some of the pros. At test time, you're using the same learning rule as reinforcement learning. So you're just starting from your initialization and then running reinforcement learning. So what this means is that if you see a new task that is far outside of your representation, you can actually still learn that using the same update rule, and because you're just running reinforcement learning. And you can also achieve few-shot adaptation. So you can, with this very small amount of experience, it can adapt its policy very quickly. And then one of the limitations is that you need to actually have a number of tasks that you're training on at training time in order to be able to learn this sort of behavior and this sort of adaptation. OK, so some takeaways from this lecture for achieving transfer. First, the most popular reinforcement learning benchmarks do not evaluate for generalization or for transfer. Instead, they evaluate for mastery. And I covered four approaches for transfer and reinforcement learning. Task representation, representing the task in the observation, diversity, reusing representations, and meta-learning. 2 things that I didn't cover that are big topics in this area are catastrophic forgetting and the options framework, which we could actually, I mean, they're big enough topics that we could actually have an entire lecture on them, but unfortunately didn't get to cover in this course. And then next time we will have Quackley and Barrett from Google Brain. So I'll see you on Wednesday.